Yeah, so hi, thank you for the introduction. I appreciate it. So my name's Christopher Grayson, and yeah, like Maria said, I just joined the NAPLIFE project, which I guess you guys have probably heard of before. You've probably had some lectures here before on NAPLIFE. I'm very excited to be a part of it. I came all the way from the United States to study nanoplasmonic fusion. So I'm actually going to talk about the research that kind of led me to study fusion, which is more a theoretical analysis of dense relativistic matter antimatter plasmas that I did during my PhD. So my research interest started in modeling the electromagnetic fields of mostly heavy particles, external perturbations, and extremely dense plasmas. So in our first article, we developed a current conserving covariant relativistic linear response theory or method to calculate electromagnetic fields in plasmas using the Vlasov-Boltzmann equation. The fact that we included collisions for dense plasmas is very important because it allows for the plasma to have a finite conductivity. You can't have a finite conductivity without damping or collisions. We went on to apply this theoretical method to calculate the electromagnetic fields in quark-gluon plasma in heavy ion collisions, and to calculate the electromagnetic field around light nuclei in Big Bang nucleosynthesis, which is relevant for how thermonuclear reactions evolved during the Big Bang. And as Maria said, I just joined the NAPLIFE project, where I'm moving to still doing theoretical analysis, but also starting to do particle and cell simulations. So just to give you an example, just basic background, a plasma is a high temperature state of matter, which is composed of charged particles. These particles are ionized due to the high temperatures present. This makes the plasma conductive and thus very responsive to electromagnetic fields. And I have an example here, just a little GIF image of the BBM plasma, where my interest in these plasmas is normally to consider some external perturbing field, driving field in the plasma, which is often generated by inhomogeneities or heavy particles that are moving through the plasma. So I'm going to go through the background theory that we looked at for calculating electromagnetic fields in relativistic collisional plasmas. Then we're going to apply this to the magnetic fields in heavy ion collisions and to the to electron-positron plasma in a BBN, Big Bang nucleosynthesis. So just starting off, our description of the plasma, we start off with an infinite and homogeneous plasma. Fills all space and there's no inhomogeneities in it. We describe this plasma with just some equilibrium density using the phase space density. The phase space density is just the density in position in momentum space, not just in position. Where we choose some distribution over momentum. An example would be the Fermi distribution, where we have the momentum of particles in the plasma, the forward velocity of the plasma, be it like a global or a local forward velocity, and the temperature in the plasma. So then we consider some external perturbation in the plasma, which represents a small change. We'll assume a small change away from equilibrium, which we represent as delta F, a small change in the phase space density. This causes a redistribution of particles in the plasma. It causes a polarization, which introduces a polarization current. The polarization current can be described by this small fluctuation in the phase space density. In the limit that the perturbation is, the response of the plasma is much smaller than the initial perturbation, we can use what's called linear response theory. In this limit, the polarization current is related to an electromagnetic field causing the perturbation by just the linear polarization tensor. For stronger fields or a more responsive plasma, you would have higher order of polarization tensors. And this is written in a Fourier space. In the position space, it would be a convolution integral of the tensor in the field. So let me go back here. If we use kinetic theory to find this delta F, this change in the phase space distribution, we can calculate a polarization tensor for that plasma, which then can be used to calculate the electromagnetic fields in this plasma, which are very important for the behavior of the plasma from some perturbation. So we need to figure out how to find this change in the phase space density by introducing some kind of external field in the plasma. We do that by solving the Vlasov-Boltzmann equation for the plasma. The Vlasov-Boltzmann equation is actually a system of differential equations, integral differential equations describing the plasma. You have an equation for each species. You have a flow term, which is just diffusion of particles through the plasma. They're moving because they have kinetic energy. You have a force term, which is just the Lorentz force on particles on the plasma. If they're charged, there's an electromagnetic field present. And then you have the collision term, which describes microscopic collisions between all the particles in the plasma. So most of the complexity of solving the Vlasov-Boltzmann equation comes from the collision term. The collision term is this complicated integral over all possible collisions that can occur between particles in the plasma with this transition rate, which is basically just describing the type of reactions that can occur when these particles collide. So it's very complicated if you have many different reactions and many different particles. So a common simplifying assumption people make is to use what's called the relaxation time approximation for the Vlasov-Boltzmann equation. So in the relaxation time approximation, we basically just say that if the distribution of the plasma is evolving, it's going to return to equilibrium to maximize entropy. And it returns to equilibrium in some characteristic time tau, which is basically just the mean free time between collisions in the plasma. And I'm going to talk about this parameter tau often as a 1 over tau, where we call kappa the damping parameter. It's basically just calculating a representation of how much damping there is in the plasma. One issue with this, we call it the Anderson-Witten collision term, is that it relaxes all quantities of the plasma in time tau. This is unrealistic because there are conserved quantities in the plasma that should not change with time, like current and momentum conservation. These should be constants and shouldn't change at some arbitrary set time scale tau. So a lot of work is done to correct this relaxation time collision term because it's one of the best ways to, the simplest ways to simplify the calculation of the Vlasov-Boltzmann equation. There's many corrections you can add to correct for energy non-conservation, momentum non-conservation, current non-conservation. So the one we looked at in particular, because we were interested in dense plasmas, is adding a correction which accounts for current conservation. So this is a relativistic generalization of the BGK collision term, where they were the first ones to propose adding this term, which corrects for current conservation, which you can actually, if you plug this into the Boltzmann equation and then integrate, you can instantly see that this is basically adjusting the change in equilibrium so that it's always satisfying current conservation. So now that we've simplified the Boltzmann equation while retaining current conservation, we can Fourier transform the whole Boltzmann equation, Vlasov-Boltzmann equation, because we assume that the plasma is infinite and homogeneous, and solve for delta F, the change, the perturbation in the plasma due to adding this electromagnetic field. We can just solve for it algebraically in Fourier space. Very simple. Then we can calculate the induced current from this delta F in Fourier space that we found. We'll then use that result to identify the polarization tensor, because we know that this integral of the Fourier transform of delta F should be related to the polarization tensor, where we'll see when we calculate the electromagnetic fields in a plasma that the polarization tensor is describing the response of the plasma to these electromagnetic fields. So for this Boltzmann equation, we calculated this polarization tensor. I don't show these are integrals. These R mu nu, Q nu, Q mu, H mu nu, and all that, which can be evaluated for some equilibrium distribution, but they're very complicated. If you want to look them up, you can look at them in this paper here. But I'll talk about this equation a little bit. So the first term, R mu nu, is actually related to the relaxation time approximation I was talking about, which doesn't conserve current. That's the first term here. And then we have this current conserving correction, which has this extra term due to the current conserving piece here. Another thing I want to mention is that if you just look at R mu nu and take the limit of damping go to 0 with a small imaginary piece to retain Landau damping, you get R mu nu, or you get what you would have for a collisionless plasma. A collisionless plasma, again, has an infinite conductivity and it has a collision term of 0. So another thing I want to say about the polarization tensor, we'll see some forms of the polarization tensor for different equilibrium distributions. I'll actually calculate those integrals and stuff and show you the result. Well, calculated them another time. I'll show you the results though. I want to mention though that overall the polarization tensor, the strength of polarization in the plasma is related to the Debye mass squared, where it basically represents the strength of screening in the plasma. So the Debye mass, you may not have heard of a Debye mass, but you've definitely heard of a Debye length, where the Debye length is the characteristic distance of screening in the plasma, where it's basically if you have Debye-Huckel screening or static screening or like a Yukawa potential, it's the rate of exponential decay of the field, the Coulomb field in the plasma. So this describes, this mass describes the strength, it's an energy scale that describes the strength of screening. So what I just described is kind of like a way to calculate the polarization tensor for a particular plasma from the Blazol-Boltzmann equation. Now we're going to look at actually calculating the electromagnetic fields in some general infinite homogeneous medium. So that would be represented by this polarization tensor here, pi mu nu. So if we take the linear response equation, we have Maxwell's equations of the plasma, which has the external current that we're using to perturb the plasma, and then it has an induced current, which is representing the polarization response of the plasma. We then write the induced current in terms of the linear response relation, and then we can basically, in Fourier space, just solve algebraically for the potential. And we actually refer to this as the self-consistent potential, because you could do something like iteratively insert and calculate the potential by putting in the induced current using the external field and updating the value of the field each time. But this, you don't need to do that. You can just solve both sides of the equation at once and get the self-consistent field, which includes all orders of back reaction of the polarization on the external field. So in order to solve this, equation here, we have some 4 vectors here. So we want to project these 4 vectors into a space where this equation is a little bit easier to solve. And one of the most useful projections you can do in this case is to project your coordinates onto the direction of the 4 potential, the electromagnetic 4 potential, in terms of the wave vector k. So we have a parallel component to the polarization, or the electromagnetic potential, and then we have a transverse piece to the electromagnetic potential. So in these coordinates, the polarization tensor takes on this form. And as you can see, it's only dependent on 2 parameters or functions: the perpendicular or transverse longitudinal transverse polarization function and the parallel or longitudinal polarization function. So if we think about what this projection would look like for like just a light wave going through the plasma, the light wave has perpendicular EMB fields and only samples the perpendicular polarization function. So this perpendicular polarization function is kind of describing the propagation of light. It's also related to the magnetic field in the plasma. The longitudinal polarization function is related to charge fluctuations in the plasma, and it's related to the rest, basically the Coulomb field of charges in the plasma. So after performing this projection, you can solve Maxwell's equations, including the induced current, and get these formulas for the self-consistent fields. So we have the scalar potential, which is just the electromagnetic potential. It's related to the polarization, longitudinal polarization function. This second piece in parentheses is actually just the frequency and wave vector dependent permittivity in the plasma. And same here, this A perpendicular, you can rewrite it in terms of a position dependent, position and frequency and time dependent permittivity. And then the last piece, the parallel component of the potential is just given by the Lorentz gauge. So now if you've used the Vlasov-Boltzmann equation to calculate the polarization tensor for your particular plasma, you can use these self-consistent potentials, electromagnetic potentials, which are in Fourier space, to calculate the potentials in Fourier space. You just plug in the polarization functions, which come from the polarization tensor. Then, in order to get the electromagnetic fields, you just algebraically calculate them in Fourier space and Fourier transform back to position space. So that's kind of the whole process that you go through to calculate the electromagnetic fields in a plasma, in a relativistic plasma. So now I'm going to go on to talk about applying this polarization tensor to calculate the electromagnetic fields in quark-gluon plasma during a heavy ion collision. So in heavy ion collisions, there are some of the largest electromagnetic fields in the universe. The electric field is above the Schwinger limit, which is the electric field at which the vacuum breaks down and forms electron-positron pairs. And the magnetic field is comparable to the magnetic field in magnetars. The magnetic field in a heavy ion collision is actually pretty simple to calculate. You can just take a charge that's at rest, boost it in the direction of motion, and using the right-hand rule, you get a circulating magnetic field. When these heavy ions collide in the region of overlap, they form a quark-gluon plasma. And as the particles separate, this quark-gluon plasma introduces eddy currents, or sorry, the field introduces eddy currents in the quark-gluon plasma, the magnetic field. And these currents generate another magnetic field, and the total magnetic field in the plasma is responsible for polarization, spin polarization of hadrons when this quark-gluon plasma eventually hadronizes, breaks up into hadrons. Yeah, so we're interested in how does this magnetic field evolve in QGP, how does it impact the hadron spectrum? So this has actually been explored experimentally very recently after we published our results for the magnetic field in quark-gluon plasma, which I was really happy to see. And they provided constraints on the electrical conductivity of quark-gluon plasma. So I want to, so let's address some of the simplifications we're making here by applying this method. So we're actually, if we use the method of calculating electromagnetic fields that I just described, we're basically assuming the quark-gluon plasma is filling the whole universe when a heavy ion collision is happening. Obviously, the quark-gluon plasma is actually very small. It just fills the region of overlap between the heavy ions. So we're neglecting boundary effects at the surface of quark-gluon plasma like skin depth. We're also neglecting the rotational behavior of quark-gluon plasma when they collide, but we'd like to introduce both of these two concepts in future work. Another thing I want to mention is that we're not studying the transport of QCD particles in quark-gluon plasma. We're looking at how an electromagnetic field interacts with quarks in the plasma. So just studying electromagnetic forces in quark-gluon plasma. And we're making the assumption that the damping, which is going to enter the Vlasov-Boltzmann equation, is coming from QCD, not from QED, because the QCD force is so much stronger than QED. So we're imagining an electromagnetic perturbation of a QCD damped plasma. So for quark-gluon plasma, you have a system of Vlasov-Boltzmann equations with a QCD damping. You have a Vlasov-Boltzmann equation for each quark species, and we consider up, down, and strange at a temperature scale of 150 to 300 MeV. That just comes from the mass, what the masses of these quarks are. And when you sum up what the induced current should be in this plasma, you effectively just get a factor of 2, which is underlined in this corner over here, where if you remove the factor of 2, this would be the Debye mass in a usual ultra-relativistic Debye mass in a usual electron-positron plasma. This extra factor of 2 basically comes from summing up the fractional charges of the quarks and having the extra number of species in the plasma to create a polarization current. So in order to calculate the polarization tensor, we need to assume an equilibrium distribution function, which will perturb the plasma from. And we assume a Fermi distribution, where we take the ultra-relativistic limit because the temperature is so high in comparison to the masses of these quarks. And this neglects the thermal mass that quarks acquire in quark-gluon plasma. But we needed to do this in order for it to be analytically solvable. So in the ultra-relativistic limit, the polarization tensor, those integrals that I showed, or the formula that I showed in the previous slide, you can calculate the longitudinal polarization function and the transverse polarization function to get this form. And the transverse polarization function is going to be of interest to us to calculate the magnetic field in the plasma generated by the heavy ion collisions. So now that we have this polarization function for an ultra-relativistic quark plasma, electromagnetic quark plasma, we need to estimate this damping parameter kappa. So we use this estimate from Gulaschi and Rovchinsky, which is basically they are interested in calculating the mean free time of quarks in quark-gluon plasma as a function of temperature. And then we created, we used this fit for the running of the strong coupling as a function of temperature, because it changes with temperature. And we got that using this estimate, the value of damping in the plasma is much, much stronger than the characteristic scale of energy of screening, which is the Debye mass. So the Debye mass is also related to the plasma frequency, which describes the characteristic rate of oscillations of plasmons in the plasma. And one thing you can notice about this formula is that if kappa is larger than 2 over the square root of 3 times the Debye mass, this whole formula becomes imaginary. And so you get over-damped oscillations in the plasma. So we expect to see over-damped behavior in the magnetic field. So when the magnetic field hits a peak, it will just decay down exponentially and it won't oscillate in the plasma. We wanted to check if this estimate of kappa was actually good. So we compared it to, we calculated the static conductivity of our quark-gluon plasma. So we have the Debye mass from our theory, and we have kappa from our estimate. And we can actually use this to calculate the electromagnetic conductivity of quark-gluon plasma, which is something that people want to measure in experiment in heavy ion collisions. We compared it to lattice QCD calculations, and we actually got that this estimate was pretty close to lattice QCD calculations, even though we got a static conductivity to use for our calculation to be around 5.01 MeV, which I think is a little bit high as compared to what people currently use. So now that we have the damping parameter, we can actually calculate the magnetic field by doing this Fourier transform back to position space using the polarization function for the plasma. So we do this for a couple different models, because when people calculate the magnetic field in quark-gluon plasma, they use all sorts of different models to do it. We have a fairly complicated one here, and we want to see what limits actually model the magnetic field in quark-gluon plasma accurately. So we have the full time and space dependent of response, which is basically just a numerical, you numerically integrate this function up here, numerically Fourier transform. Then we have one where we neglect spatial dispersion or the spatial dependence of the electromagnetic field perturbing the plasma, which is basically like the Giroud model of electrical conductivity. And then we have the static conductivity, which is effectively like including Ohm's law into Maxwell's equations and then solving Maxwell's equations for the plasma. Before we wrote this paper, the common theoretical way to model quark-gluon plasma was to use this static conductivity. Another interesting model we found to use was to use the light cone conductivity. Basically, since these ions are traveling at near the speed of light, they only really sample the plasma along the light cone. So the light cone conductivity, if you look at this gray line here, actually fits the full space-time dependent response pretty well. And you'll see in the next plot that it does at all times. So this is fairly early times in a heavy ion collision. The one thing I want you to notice in this plot is that the static conductivity does not really describe the early time behavior of the field well. And this is just because it's a static theory. It doesn't, it's not sensitive to space and time dependence of the field. So here's more of a longer time scale evolution of the magnetic field in quark-gluon plasma. So there are a couple time scales I want to talk about in this plot that are relevant for a heavy ion collision. So when you have a heavy ion collision, you have the two heavy ions coming and passing by each other. They're Lorentz contracted, so that collision time is on the order of 2r divided by gamma. Then you have a relaxation time, which is basically the time scale at which this plasma is equilibrating. And then we have the time scale at which the magnetic field matches the prediction of what you would get if you used a static conductivity, which is actually at fairly late times. Even though it gets pretty close beforehand, this is the magnetic field that you get if you use a static conductivity. Then we have this freeze out time, which is very important because this is when, as quark-gluon plasma cools down, this is the time at which it's cooled enough that it will actually form the final hadron spectrum that you'll measure in a particle collider. And we're interested in how this magnetic field might impact this final spectrum. So now I would like to, basically the experimentally important part of this magnetic field is what is the magnetic field at freeze out, at the time where we generate the hadron spectrum from quark-gluon plasma that we're actually going to measure. So we wanted to look at this magnetic field, and we're really interested to find that this magnetic field did not depend strongly on the energy of the collision of the heavy ions. So you can see for a range of values of gamma, which is related to the collision energy, at very large values of the Lorentz factor gamma, you get almost the exact same magnetic field as a function of time, granted at the same temperature. And we use the light cone conductivity that I was talking about before that fit the magnetic field fairly well to calculate an analytic solution for the late time magnetic field as a function of the damping parameter, which is shown as a black line. So it fits the large gamma result. So one thing we can notice in this plot is that if the freeze out time is smaller, you get a larger freeze out field. And that's actually more important than what the collision energy is. So it's kind of counterintuitive to what you would think. You might think that at a higher collision energy, you get a bigger magnetic field, so you should get a bigger freeze out field in the heavy ion collision. But actually, since the freeze out time decreases as the energy in the collision is lower, you get that for lower energy collisions, there should be a larger freeze out magnetic field in the plasma than at higher energy collisions. So this is a lower energy or a higher energy collision on the left side here, which has a larger peak field but a smaller freeze out field. And on the color scale is the same. And on the right side, we have lower energy but a larger freeze out field. So this was interesting because this is actually what they noticed in that experimental paper where they're studying the directed charge flow in quark-gluon plasma. They found that the charge splitting was larger at lower collision energies, indicating that the freeze-out magnetic field would have been larger at lower collision energies, which I thought was interesting. So there are a number of improvements we could make to the study of the electromagnetic fields in quark-gluon plasma, but some in particular are we want to include realistic space and time dependence in quark-gluon plasma, which would be something like having the plasma form at the time the ions collide, having a realistic shape to the edges of the plasma, and then also to include rotations and also spin transport in quark-gluon plasma. not just charge. So now I'm going to go on to talk about how we can use this plasma theory to calculate some results in Big Bang nucleosynthesis. So this whole portion was only really about we're only looking at the magnetic field, so it was only dependent on the transverse polarization properties of the plasma. But now we're going to look at the potential in the plasma, which is related to the longitudinal portion of the polarization function. So during the lifetime of the universe before recombination, the universe was filled with a dense plasma. You know, there was all sorts of phases to this plasma. But during Big Bang nucleosynthesis in particular, which is a time period around 100 seconds to 300,000 years after the Big Bang, there was a dense electron-positron plasma present that was basically just left over from the Big Bang. So we're actually going to focus on a smaller time scale, which is 2 to 20 minutes after the Big Bang, which is when most of the fusion reactions during Big Bang nucleosynthesis occurred. So Big Bang nucleosynthesis is basically that the universe was hot enough and at the same time cool enough for light nuclei to form, but still have enough kinetic energy to undergo fusion reactions. These fusion reactions generated distributions of light elements, which in principle we can still measure today. It's not the absolute abundances of these light elements because other stuff was produced in stars and supernova later, but they would be the primordial light element distributions, those just coming from the Big Bang. So in order to estimate these primordial light element abundances, we have this complicated fusion reaction network, which we can use to estimate the primordial light element abundances. So it's becoming more and more common to imagine this reaction network in the dense electron-positron plasma that was present. There's still some questions on how maybe this actually affects the reaction network, but there are still a lot of open questions that remain about the standard BBN reaction network. So one of our collaborators, Cheng Tao, calculated the electron-positron plasma during Big Bang nucleosynthesis during this, and we're interested in this time scale in between these two vertical dotted lines, which is the 86 to 50 keV mark. This is where most of the fusion reactions are occurring that we're interested in. And the density of this plasma is actually much, much larger than the density of the solar core. So it's very dense. Another thing I want to note is that while we have this very large electron-positron density, we have a fairly low baryon density, where by baryon density, I just mean the density of lighter nuclei in the plasma. So we can think of these light nuclei as dispersed impurities in the electron-positron plasma. Another thing we can notice is that this red line is actually two lines on top of each other. It's the electron and positron density. They're right on top of each other because the number of electrons and positrons is the same up to 20, down to 20 keV where they split. And this is important because it allows us to assume that during BBN, in between these two dotted lines, there is effectively negligible chemical potential. Oh, my GIF's not working that well. So this gives us this picture that we have fast-moving, dense electrons and positrons moving around, and slower, heavier, light, more dispersed light nuclei, which are undergoing fusion reactions. So let's talk about exactly how a plasma is relevant for BBN, Big Bang nucleosynthesis. So if you have a light nuclei sitting in electron-positron plasma, it acts like an external perturbation, like I was talking about before with the delta, the change in the perturbation in the phase space density, because it's generating this electromagnetic potential around it, just a Coulomb potential. The polarization in the plasma changes this field to Debye-Huckel screening, which reduces the electrostatic repulsion between charges in the plasma. This reduction in the Coulomb potential effectively makes it easier for the ions to get closer together. And it increases what they call the probability, the Coulomb penetration probability, which is the probability that the ion can tunnel through the internuclear potential and reach the deep, strong nuclear attraction portion of the potential and undergo a fusion reaction. So this enhancement of the Coulomb penetration probability and the reaction rate of the fusion reaction changes how you would changes from vacuum how you would expect these reaction rates to appear. And it doesn't just increase the distributions of all these light nuclei, because it's a complicated network. So if you increase the abundance of one, it's going to change the other one. It's changing the network in a complicated way. So there are a couple of different models people use to study screening. So originally, screening effects on thermonuclear actions was used to study in the cores of stars. And originally, just static screening was used, or a Debye-Huckel potential was used to describe the field in a plasma, which is applicable for just static charges that are stationary, that aren't moving. Then some calculations were done for dynamic screening, which basically accounts for the motion, the thermal motion of ions in the plasma. So they can develop something like a wake field, a wake of charges moving behind them as they move through the plasma. But this was done for no damping, no collision. So it's effectively using an infinite conductivity for the plasma. So we use this relativistic currents-conserving Vlasov-Boltzmann equation with damping to calculate damped dynamic screening, which is basically dynamic screening but including damping in the plasma, which allows you to have a finite conductivity, which is really important to make the plasma have more like physical properties. So we also have a system of Vlasov-Boltzmann equations for this plasma. We have an electron, positron, and a photon Boltzmann equation. Now the photon Boltzmann equation does not couple directly to electromagnetic fields. A photon doesn't interact with an electric field except for at extremely high electric field strengths. So it can only couple through the collision term. And again, the potential is going to be related to the longitudinal permittivity, which is related to the longitudinal polarization function. You can analytically calculate the longitudinal polarization function in the non-relativistic limit. And we'll use that since the temperature in BBN is much, much less than the mass of an electron. So they're moving non-relativistically. And in the non-relativistic limit, the plasma frequency is related to the Debye mass by effectively the thermal velocity. So our collaborator, Chengtao Yang at the University of Arizona, calculated the damping in the BBN electron-positron plasma by considering the most probable 2-to-2 QED scatterings in the plasma. And where the total kappa is shown in black. And we can see that, again, we have an over-damped plasma because the damping rate is much, much larger than the Debye mass, or I guess really the plasma frequency. Another thing I want to mention is that the rate of inverse Coulomb scattering, so the rate of energy and momentum transfer from photons to electrons and positrons in the plasma, is fairly small in comparison to the other processes present. So we're going to neglect the contribution of photons to this plasma. But the photons are very important for other aspects of BBN. So by expanding the polarization function in the limit of large damping and small velocity, you can calculate an analytic result for the potential in BBN. One thing I want you to notice is that it has this cosine of psi here, where psi is basically the angle between the direction of motion and the direction of observation. And so we're developing an anti-symmetric potential. So we're actually really interested to see that this potential had actually been calculated before, but in a completely different field of physics, still plasma physics, but it was in the study of dusty plasmas, which they're actually interested in some laboratory plasmas and plasmas in the ionosphere of Earth. But they're studying a similar situation where they had heavier impurities moving around in a less dense a plasma medium. So let's look at this potential. So here we're comparing to the dynamic screening calculated by Huang in 2021. So the damped dynamic screening, the one that includes damping, predicts a very similar potential, but it's just slightly less screening due to the damping present in the plasma. But you have this negative portion of the potential. So there's enough screening in the front that the potential is actually going negative in the front and it's positive behind. It's kind of interesting. And then this approximation that I showed you on the last slide for the limit of large damping and large and small velocities matches the numerical result pretty well for 100 keV, which we used for comparison. And then this is the dusty plasma result, which they were only interested in large distances for their calculation, so it matches at large distances. So we realized in this calculation that all of these theories of plasma screening, we're actually calculating in what's called the weak field limit. And we realized that the short range potential, which is the portion of the potential relevant for quantum tunneling for a fusion reaction, you get very close before you quantum tunnel through. So you probe the short range behavior of the electromagnetic potential. This actually does not satisfy the weak field limit. So we wanted to go and check if corrections from strong screening could change the short range potential. So the BBM plasma is globally a weakly coupled plasma. Basically, a weakly coupled plasma means that the Coulomb energy for a charge compared to the thermal energy is small. So it's dominated by thermal fluctuations and not Coulomb attraction or repulsion. But as you get closer and closer to the nucleus, the potential, so if you look at the distribution of energy of particles in the plasma and the probability of them to tunnel through the Coulomb barrier, you get what's called the gamma peak, which is the most probable energy at which these particles will tunnel through the barrier. If you look at a particle coming in at the gamma energy, it's probing the electromagnetic field, the potential around another nucleus, when the potential is much, much stronger than the thermal energy. So we wanted to look at corrections to the potential due to the Coulomb energy being larger than the thermal energy. So the basic theory of how strong screening can change a potential is it changes the equilibrium energy of particles in the plasma by considering the work done by the potential, the gain in energy from the external field on the particle. And in the Boltzmann limit, you get that it's just an exponential increase in the density around that charge. So normal Debye-Huckel screening would give you like this, would give you, I guess it's actually almost constant, but for strong screening, you get an exponentially enhanced screening close to the nuclei, where there's a potential present. So there's a history of studying strong screening because it's relevant in white dwarfs, which are like a carbon-12 plasma, which is strongly coupled globally, not just locally. But they actually use a fairly different method of calculating strong screening effects, where we're actually just solving the Poisson-Boltzmann equation, which basically reduces to the Thomas Fermi approximation at low temperature. Sometimes it's called intermediate screening, but it really connects the strong screening and the weak screening regimes. It can describe both. So it should just be called, I don't know, general screening or something like that. But we call it self-consistent strong screening because you have to self-consistently solve for the potential when you apply this theory. So basically the way that you do this is you just solve for the Poisson equation. You solve the Poisson equation, including the induced charge density in the plasma, where we have an electron-positron plasma again. So you can either use Fermi or Boltzmann statistics to describe the distribution of particles in this plasma. And we use a Gaussian charge distribution just to make it analytically solvable. So we recast the Poisson equation to make it look very similar to the Debye screening equation, where if this mass here didn't depend on phi, if it was just the regular 1 over the Debye length squared, this would just give you the Debye-Huckel formula when you calculated it that I've shown on some previous slides. This allows us to compare the strength of screening in in between different theories. So this M squared describes the strength of screening, and we can compare to the weak and strong and use different distribution functions to describe the plasma. So as I said before, in the weak limit, you get just normal Debye-Huckel screening for the Debye mass, which gives you this constant line at 3 keV. That's the strength of the Debye mass in the BBM plasma. If you use Boltzmann screening, you get this huge exponential increase in the strength of screening in the plasma, which looks a little unrealistic to me. It's like going to a crazy high keV, which would create a huge change in thermonuclear reactions. I want to also mention these two vertical lines on here. One is the gamma energy, which you can imagine is the energy most likely for particles to tunnel. And one is the potential at the origin. So in between these two lines is kind of where we'll have a screening mass related to quantum tunneling. So if you use Fermi-Dirac screening, you get these cinches and Koches just because if you have electrons and positrons, they both have exponential distributions. When you combine them, you get a hyperbolic function. Gives us a more suppressed Debye mass even at large values of the potential because of stacking of the. It's accounting for stacking of the fermion states. We also noticed that if you can perform this integral directly in the ultra-relativistic limit to give this formula, which has been derived a few times before, but not really noticing. Normally, it's derived with phi being chemical potential because it's kind of like a position-dependent chemical potential. But here, you can see that it can be thought of as the actual potential generating this Debye mass. So and I also want to mention that this simpler formula for the Debye mass describes the strength of screening very close to the nuclear surface. So the method of calculation is we know an analytic solution to at large distances to the Debye-Huckel equation. So globally, the plasma is weakly coupled. So we have an analytic solution by solving this differential equation at large distances. And then we create a shooting method where we shoot inwards towards where the strong screening is applicable to get a solution for the short range potential, where our shooting parameter is basically the effective charge seen at large distances. And we're also using that the electric field has to be 0 near the origin. So when you calculate this, you get this interesting step shape in the potential very close to the nuclear surface, which is basically coming from Fermi-Dirac statistics. We get this is for alpha nuclei, so we have a very small change in the internuclear potential, but this is to be expected because helium abundances kind of match what's theoretically predicted, what's observed and predicted kind of match. One important thing to mention, though, is that Boltzmann statistics vastly overpredicts the internuclear potential. It's much, much larger than you would expect. So it's really important to use Fermi-Dirac statistics when you perform these calculations. And it's basically because the large value of the potential is making the density huge. So here is it as a function of temperature. So we can see that basically the total amount of the potential related to the screening charges is increasing as the temperature increases because the Debye mass increases linearly with temperature. But the change between weak and strong screening, where weak screening is the dashed line, and then strong screening plus weak screening is the solid lines, is increasing at lower temperatures. This is because the strength of strong screening is controlled by this phi over T parameter, which is increasing at lower temperatures. So we also we went ahead and looked at how this potential would impact reaction rates, which is again through the Coulomb penetration factor, which is basically just the WKB integral between the two turning points as the particle tries to tunnel through the Coulomb potential. And so for normal static screening, you get this exponential enhancement in fusion reaction rates, which is related to Z1, Z2 times alpha over temperature times the Debye mass. And then this is the contribution from damp dynamic screening in the limit of large damping and slow velocities. So this actually predicts suppression in nuclear reaction rates, not enhancement, but from the minus sign. But one interesting you can do with this is you can write these parameters here as a conductivity of the early universe, which is kind of interesting to think if that could be measured. So I'm running out of time, so let me skip some stuff here. So this is the actual reaction rate enhancement for a carbon-12 reaction as a function of temperature. The orange area is the BBN temperature range. And one thing I want to mention is that these enhancements are often calculated using the potential at the origin. Excluding the position dependence of the potential. But if you remember, the potential had this pronounced step shape to it. If we just use the potential at the origin, it gives us, which is the orange line, the orange dashed line, it gives us a huge overestimate in comparison to the actual result, which is the blue dashed line. This is the enhancement in the reaction rate as compared to weak screening, which is the black line for strong screening. And this effect is kind of interesting because it doesn't affect light nuclei, but it affects heavier nuclei. And this is a comparison to previous strong screening models that is used for white dwarfs. But they don't match very well because they're not really applicable for globally weak plasmas. So just to summarize, I went through the calculation of this current conserving polarization tensor, relativistic polarization tensor with damping, and we applied it to quark-gluon plasma and Big Bang nucleosynthesis to get these analytic formulas for the magnetic field in quark-gluon plasma and for the enhancement factor for damped dynamic screening in BBN. Some improvements we'd like to make. So for quark-gluon plasma, we want to have how spin is transported in the plasma. We want to improve the collision term by making it conserve energy, and we want to have realistic boundaries for the plasma, like having it like a cylinder in space and having it have a finite lifetime. And for this strong screening, we're interested in creating a combined dynamic and strong theory, but there's some theoretical difficulties in generating that. And we're also interested in studying strong screening in the case of having very, very heavy nuclei present in the plasma. So like in the NAPLIFE experiments, we have these gold impurities in an electron plasma, which in principle from strong screening can generate a very large electron cloud. So we're interested in studying how that can change fusion reaction rate. So thank you for your time. It was an honor to be here, and I appreciate any questions.